For a traveling wave, the wave function generally looks something like an amplitude A, and then a sinusoid, but it's not just a sine or cosine, but rather the e to the I. And since this is a traveling wave, let's say moving to the right, it's just going to look like kx minus omega t in the argument here of this sinusoid. What would the absolute value squared of this thing look like? Well, it would be the absolute value squared of that constant a, which it can be itself complex, although it is a constant in x and a constant in t. And it equal e to the I kx minus omega t, e to the minus I kx minus omega t. And this just comes from the fact that the absolute value squared of a complex number is equal to its complex conjugate times itself. And if you remember, a complex number can be represented by an amplitude phase. So our norm is z times e to the I theta. But here, if we look at what's in this exponent, I have e to the I theta and I have an e to the minus I theta. When I multiply two exponentials together, I add their arguments together, so I have positive something plus negative something. This will just equal e to the I times 0, and that's just 1. Well, for a traveling wave, it has a somewhat pleasing outcome that the amplitude squared or probability squared would be, the probability would be just a constant independent of x. Because in the case of a traveling uniform beam, I would think I'd have a uniform probability of finding it anywhere along the x-axis. For a bound state, this is a completely different example. Before I had a traveling wave, now I'm going to talk about a bound state. We remember that the wave function always has to have the form capital psi of x and t is equal to some function only of x, which I'll write as little psi of x, e to the minus I omega t. That's the general form for a bound state, where you will show on the homework that solutions to the Schrödinger equation, i.e. states of definite energy, for a bound state are always going to be separable. The spatial parts can be separated into one function, the time-dependent parts can be separated into another function, and the time-dependent part is always this exponential e to the minus I omega t. In this case, psi of x and t norm squared is just going to equal psi of x squared, and notice that this is not dependent on time. So again, we have something that maybe makes sense in an intuitive way. The bound states have a spatial distribution of probability density, and that probability density doesn't evolve over time, and that's why sometimes bound states are also called stationary states. That's borrowing a term that Niels Bohr gave to the electrons in an atom occupying certain radial orbits. They were stationary for his model because he wanted them not to cascade and collide with the nucleus, but we're calling them stationary here because they don't evolve over time. They stay parked at a certain spatial distribution.